this video, we will learn something called a symmetric matrix. Yes, a symmetric matrix. When can we say that a matrix is symmetric? Matrix A is symmetric if A transpose is equal to A. Understand this well. The transpose of the matrix is equal to the matrix itself. This is the definition of a symmetric matrix. Look at this matrix A. Is it symmetric? What does the definition say? It will be symmetric only if its transpose is equal to itself. So what is A transpose here? We interchange the rows and columns. We get A transpose as 1, 2. The first row became the first column and the second row became the second column. Are they equal? When are two matrices equal? Do you remember equality of matrices? Two matrices are equal if they're of the same order and if their corresponding elements are equal. Here the orders are different. The order of A is 2 by 1 and that of A transpose is 1 by 2. They are not equal. Because A transpose is not equal to A, we say that A is not a symmetric matrix. That's how easy it is to find out if a matrix is symmetric or not. We find its transpose and check if it's equal to the original matrix. If not, then the matrix is not symmetric. Let's take another example. Here's matrix B. Is matrix B symmetric? Pause the video and find out if B is a symmetric matrix. To know if B is symmetric, we find B transpose first. The first row becomes the first column, 1, 4. The second row becomes the second column, -1, 2. And the third row becomes the third column, 0, 3. This is B transpose. Are B and B transpose equal? The order of B is 3 by 2 and that of B transpose is 2 by 3. As the orders are different, they are not equal, which means B is not a symmetric matrix. This should give us a hint. Tell me, can a rectangular matrix ever be symmetric? A rectangular matrix is a matrix in which the number of rows is not equal to the number of columns. Can it ever be symmetric? No chance, because the order of the transpose will definitely be different from that of the matrix. Only a square matrix can be symmetric. A square matrix is a matrix in which the number of rows is equal to the number of columns. Take matrix C for instance. 2 rows and 2 columns. This is a square matrix because its number of rows is equal to its number of columns. Is this a symmetric matrix? We find C transpose to know the answer. The first row becomes the first column, 1, 2, and the second row becomes the second column, 2, 4. Clearly the two matrices are equal. Same order and the corresponding elements are equal. 1 and 1, 2 and 2, 2 and 2, 4 and 4. Matrix C is a symmetric matrix as its transpose is equal to itself. Does this mean that every square matrix will be symmetric? Here's matrix D. It's a square matrix because its number of rows is equal to its number of columns. Pause the video and find out if matrix D is a symmetric matrix. To know if D is symmetric, we need to find D transpose first. The first row will be the first column here. 1, 3, 1. The second row becomes the second column. -1, 1, 4. And the third row will be the third column here. 2, 1, 0. Are these two matrices equal? The orders are equal, yes. But are the corresponding elements equal? Let's check. 1 is equal to 1. 3 is not equal to -1. For two matrices to be equal, all the corresponding elements must be equal. As 3 is not equal to -1, these two matrices are not equal. D is not a symmetric matrix and it is not equal to its transpose. So remember, every square matrix need not be symmetric, but for a matrix to be symmetric, it has to be a square. Like in the first two examples, the matrices were not square, so they will surely be non-symmetric. But if they are square, then they may or may not be symmetric. Here's one last example you need to solve. This is matrix E. Pause the video and find out if it's symmetric. The first thing we need to check is if the matrix is a square matrix. As it has equal number of rows and columns, we can say that it is a square matrix. So it may or may not be symmetric. To find out if it's symmetric, we need to find E transpose. This is what we get by interchanging the rows and columns of E. First row, first column, second row, second column, and third row, third column. Both matrices have the same orders and their corresponding elements are also equal. Matrix E is equal to E transpose. Matrix E is symmetric. With this, we can modify the original definition a bit. We say that a square matrix A is symmetric if A transpose is equal to A. This is a better way to understand it. If it's not square, we can directly say that it's not symmetric. And if it is square, we find A transpose and check if it's equal to matrix A. If it's equal, we say that the matrix is symmetric. We saw what a symmetric matrix is. A square matrix A is symmetric if A transpose is equal to A. In this session, we will look at what a skew-symmetric matrix is. The definition goes like this. A square matrix A is skew-symmetric if A transpose is equal to negative A. Let me repeat. A square matrix is skew-symmetric if its transpose is equal to its negative. A simple example would definitely help us understand better. Is this matrix A skew-symmetric? So we will find A transpose first and then negative of A. If they are equal, then we can say that matrix A is skew-symmetric. Let's find A transpose first. The first row becomes the first column, 1, 4, and the second row becomes the second column, 0, minus 1. This is A transpose. And what about negative A? To find the negative of a matrix, we negate each of its elements. 1 will be minus 1, 4 will become minus 4, negative of 0 is 0, and negative of minus 1 is 1. Are these two matrices equal? For two matrices to be equal, their orders have to be equal and their corresponding elements also have to be equal. The orders of A transpose and negative A are equal, but are the corresponding elements equal? 1 is not equal to minus 1. Even if one set of corresponding elements are not equal, we can say that the matrices are not equal. We don't need to check the rest. So A transpose and negative A are not equal. And hence, matrix A is not skew-symmetric. This tells us something interesting. I want you to focus on the diagonal elements of A. By diagonal, I mean the leading diagonal. Notice that the diagonal elements do not change for the transpose. 1 and minus 1, 1 and minus 1. And for negative A, just like the other elements, the elements in the diagonal are also negated. And what is the condition for a matrix to be a skew-symmetrical? It says that A transpose should be equal to negative A, which means all corresponding elements must be equal. Can the diagonal elements of these two matrices ever be equal? Let's say the diagonal elements of a matrix were 2 and 4. For A transpose, the diagonal elements would be 2 and 4, and for negative A, the diagonal elements would be minus 2 and minus 4, not equal. So if the diagonal elements are non-zero, the matrix can never be a skew-symmetric. Let's zoom out and write the condition. For the matrix to be skew-symmetric, the diagonal elements have to be 0. If the diagonal elements are non-zero, the matrix can never be skew-symmetric. Look at matrix B. Is it skew-symmetric? It is a square matrix and the leading diagonal elements are also 0. So it may be skew-symmetric. So let's find B transpose and negative B. Pause the video and try to find each. Okay, B transpose first. The first row will become the first column, 0, 2, and the second row will become the second column, -2, 0. And for minus B, we negate each element. Negative of 0 is 0, negative of 2 is -2, negative of -2 is 2, and negative of 0 is 0. Are these two matrices equal? Yes, the order as well as the corresponding elements are equal. So B is a skew-symmetric matrix. What about matrix C? Is it skew-symmetric? It is a square matrix and its leading diagonal elements are 0. So it may be a skew-symmetric matrix. We find C transpose first. The first row is written as the first column and the second row is written as the second column. This is C transpose. And what about negative C? Each element when negated gives us this. The negative of 0 is 0, negative of 1 is -1, negative of 4 is -4, and the negative of 0 is 0. Clearly, these two matrices are not equal. Matrix C is not skew-symmetric.